Terminal components are typically in direct contact with spaces and visible to the end users, which makes them a crucial part of every HVAC system. In this video, we will model an air terminal, specifically a diffuser. So continue with the file you created in the previous video, or open model air terminal in the chapter 2 exercise files folder. So at this point, launch Revit. From the family section here, navigate to the exercise files. From the chapter 2 folder, open this file model air terminal, which I already have here. Then make sure to open the reference level view. Two reference planes come with the template, and when you select the reference planes, you'll notice they both have names, and this parameter defines origin checked. So in every Revit family, only one vertical and one horizontal reference plane have this parameter checked, and the intersection of the two reference plane is the family's insertion point. For this family, we want the insertion point to be at the center of the geometry, so we'll let the two default reference planes define origin. Also, you have the is reference parameter here, which informs the priority assigned to a reference plane in the project environment by the align or dimension tools. So a reference plane can be a weak reference, it can be strong reference, or not a reference at all. So all these other ones you see here are also strong reference. So with that, we'll define the air terminals framework. So we'll start by drawing two reference planes. You can go to the create ribbon from the datum panel. You can activate reference plane or simply type RP on your keyboard. So we'll create two sets of reference planes on the sides of the default ones, making it 8 new ones. So the outer ones are for the diffuser, while the inner ones are for the neck. So quickly do that. Next, we'll select these 8 new reference planes and set their reference to strong reference so that we can dimension to them in the project environment. Then we'll activate the align dimension command from the annotate ribbon, or you can just type DI on your keyboard. Then we will draw two horizontal and two vertical dimension strings connecting the inner and the outer dimensions with the center ones. For each of them, we'll activate the quality constraint by clicking EQ. So quickly do that. After that, we will draw another two sets of dimensions. This time we'll exclude the middle planes. Next, we'll open the front elevation view. Then draw a reference plane under the reference level. So simply type RP and draw a reference plane under this. We'll dimension it to 30 millimeter. Type DI and dimension to this. Set it to 30 millimeter and lock that value. So select the dimension and lock it in place. Then we'll select this reference. Make sure that its reference is weak reference because we don't need to dimension to it. Then we name it diffuser top face. Now we've defined the framework for the air terminal. Next, we need to define the dimension parameters for the geometry. So we'll go back to the reference level. We'll select the inner vertical dimension and click the create parameter button from the modify ribbon here. Then we'll name it neck size and leave the other properties at default. Next, we'll select this inner horizontal dimension and pick the same parameter we just created. Then after that, we'll repeat the same for the outer dimensions, but this time we'll name the vertical outer dimension to diffuser height and the outer horizontal dimension to diffuser width. So now we've defined the framework. Finally, it's time to create the geometry. So to do that, from the create ribbon, launch the blend tool. Then from the draw panel here, select the rectangle tool. Highlight the intersection of the top reference plane and the leftmost reference plane. Then drag to the bottom right and highlight the intersection of the bottom reference plane and the rightmost reference plane. Make sure to highlight them. So often you don't need to lock the reference planes if you actually highlighted the reference planes. You don't need to lock the lines to the reference plane if you highlighted the reference planes when you are creating the profile. So now we've created the bottom of this blend. We need to edit the top and we'll repeat the process, but this time we'll highlight the inner reference planes. So we'll activate the rectangle tool again. This time we'll highlight the inner reference planes. Then we'll click finish to complete the blend command. Next, we'll go to the front elevation view and drag the top of the blend geometry. Align it with the diffuser top face reference plane and lock it. So now this is our blend. If you open the 3D view, you see what we've just created. It's actually inverted because the diffuser is on the other side of the ceiling surface. So next, open the family types dialog and flex the parameters and validate that they adjust accordingly. So we'll set the diffuser height and width to 300 and we'll set the neck size to 150. Now we'll close this and confirm that this actually adjusts, so you can see that it adjusts appropriately. So now that we've created the diffuser itself, it's time to model the neck. So from this reference level view, we will set our work plane to the diffuser top face. To do that, go to the create ribbon here, click on set work plane and click on this, then set the work plane to diffuser top face. Then we'll launch the extrusion command from the forms panel here and draw a circle that is centered at the insertion point. Next, we'll activate the radial dimension tool from the annotate ribbon and dimension the circle. Now we'll set the dimension. We'll create a parameter for it and we'll name it duct radius. So this is for the neck. That's where the duct will connect into. Next, we'll set the extrusion end for this to 25 minus 25 millimeter. Then we'll click finish to complete this. Now to configure a couple of more things, we'll launch the family types dialog again and we'll map the diffuser height to the diffuser width. So we'll go to the formula column here and set the value of this formula to diffuser width. Make sure the spelling is correct. And then we'll set the neck size to 2 times the duct radius. Now, if you change these values, you notice that they actually flex. You can see how everything adjusts. So that's it. We've created the basic geometry for the earth terminal. Typically, we'll still add more details to the family, such as the flow arrows. So for example, if you look at this one we have in a sample project here, you can see the flow arrows. So we'll still do this in a future video with 2D families, detail families, Also, we can configure the visibility settings for the geometry, but we'll explore this in detail in a future video. Then also, we'll still add engineering information to the family through connectors later. But finally, in this video, we'll create some family types. So if you want to create more family types, because typically for these components, you have a catalog. So I can come here and create a new type. For this what we have here, this is 300 by 300, then 150 millimeter neck size. So I can quickly come here and create a type, and I call it 300 by 300 millimeter, 150 millimeter neck size, or something descriptive. So this is a type. I can duplicate and create a new one. I can call this 400 by 400 millimeter, 200 millimeter neck size, or depending on the catalog and their sizes and whatnot. So for each of them, I can now change these values. So if I change this to 400 now, this adjusts. If I set this to 200, this adjusts. So now you can see that this is a type and this is a different type. So you can have as many types as possible. So you can also, for families that have multiple, so many types, you can even create what we call a type catalog. And for you to do that, go to the file menu here. Then from exports, you can export to family types. So this will create a .txt file, and you must save this in the same location where you have this family. So what happens is that this allows users to choose the family types to load into their projects from the type catalog. So that's it. We've created the geometry for a simple terminal component for our HVAC system. So in the following video, we will do the same for the HVAC equipment.